Right, chapter 20, electrochemistry. Basically, these slides are taken from Zumdahl's chemistry, so I want to give credit there. There's probably some stuff in here, in fact there is, from Brown LeMay's chemistry. So to give credit where credit's due. Also, a lot of the work, though, is done by myself, a lot of editing and that sort of thing. So I'm going to go ahead and go to the next slide. And that's just giving a credit to Zumdahl. Next slide. And this again is showing the two sources, Zumdahl and also Brown LeMay. Next slide. And then I myself have done a lot of the addition work here to the original slides. Next slide. All right, so for this chapter, we're basically going to be talking about not all of these topics. Basically, we're going to focus on number one, which is galvanic cells. We'll also look at concentration cells, which is number 5. I'm going to move that up next to galvanic cells. So when you're looking at the PDFs that I posted on Canvas, the PDF is going to be much more inclusive with a lot more material, and I really recommend that if you have time, you go through those because they give you several different examples of the things I'm going to talk about here today rather than just one. Let's see, now I've got to... Okay, sorry about that. All right, so we'll go from concentration cells down to electrolysis, number 10. I'll briefly talk about number 9, but then we'll move on to 10, electrolysis, and then we'll come back up to number 2, balancing redox equations. So those are the things we're going to cover here. All of these things would be covered in your lecture slides, but I'm going to cover only the things that I think are most important here in this video. So of those, the one that's by far the most important is number 1, galvanic cells. So we'll talk about that first. So let's go ahead and go to the next slide. So before we start all of this, I want to introduce why we're doing this. And so basically, very briefly, in physics, when you start talking about electricity and magnetism, basically it's like 10 or 11 chapters, and they usually start off with those 2 equations on the left in maybe the first chapter, and then the 2 on the right in maybe the 3rd chapter. And so we're not here to study physics, but I do want to point a couple of things out. So you have the Fe, which is the electric force, top left, and then top right you have the potential energy, electrical. To get from the force to the energy, you just multiply by distance. That's that ds. So the asterisk or star is multiplying by. And then to go from the force down to the electric field, and the force in the electric field a lot of the time will be written as vector quantities. They're not here. I've just written them in their form where you're showing the magnitude. So to get from the force to the electric field, you would divide by Q. So you'll notice if you go from force to U, energy, you're losing one of the R's in the denominator, so it's going from R squared to R. And as you go from the force down to the electric field, you're losing one of the Q's. So it's KE Q over R squared, where, and that arrow has a slash Q next to it. That means that you're dividing by Q. And then to go from the electric field to the voltage, you're going to again multiply by the ds. That's the differential amount of length, and different texts have different ways of writing that. Excuse me. So at the bottom right is what we're really focused in on here for this chapter, and that's going to be this thing right here, the voltage. The V is for voltage, and it's the Coulomb's constant times the charge over the distance. Now, when we talk about this in chemistry, we don't define it the same way, but it's the same thing basically. So in physics, you're talking about something's ability to push electrons through a circuit, basically, which I'll show you in just a second. So whenever you have a circuit, then they'll typically in physics or electronics tell you, okay, here's a battery, it's 9 volts. So they start from that point. And they say, okay, this, and then they start to add resistors and inductors and capacitors, and then they try to figure out what the voltage and what the amperage would be, depending on if it's in a series circuit or a parallel circuit. Whereas in this class, we're not going to do any of that. What we're going to do in this class is actually what they don't do in physics, which is to tell you where the potential comes from. And so the potential can be written with a V for voltage or an E for EMF, or sometimes they'll just write EMF. Let's go to the next slide here and look at a typical circuit diagram in a physics problem. So here at the bottom down here, this is the way they're typically written. So if you take physics, you'll see down here at the bottom they've got this E, which is standing for the electromotive force, with a plus and a negative, but they don't tell you where it comes from because it's beyond the scope of physics. They have enough already on their plate without worrying about that. So anyway, I just did all this to introduce you to why we're doing this, or at least one of the reasons. Next slide. So we want to talk about the most important thing first, and that's galvanic or voltaic cells. And we did this in the laboratory, and all we did was we basically took two beakers and we put two different kinds of metal that were electrodes in each beaker, and we connected them with a wire, and then we completed the circuit by adding what's called a salt bridge. And the salt bridge is just a way to complete the circuit. And what actually happens there is you have things that are not electrons that are migrating. So if electrons are going from left to right, then you'll have at the same time, to complete the circuit, you'll have positive ions that are going to be going in the opposite direction so that it completes the, or in the same direction actually, so that it completes the circuit. And they do that by what's called a salt bridge. So the salt bridge is part of the voltaic cell, and we're going to use the same example here that we used in that laboratory, the zinc copper cell, which produces about 1 volt. So, I mean, you can imagine this like this. If we took that zinc copper cell, and remember that we measured that at about 1.1 volts with our multimeters, and if you took 12 of those in series, you would have about 12 volts, wouldn't you? Actually, more than that, you'd have more like 13. So you might think to yourself, well, I'll just hook 12 of these together and run out to my car and put them in there where my battery is to save myself some money. But it wouldn't work, although you could probably make a battery like that, and that's kind of like the way that your battery actually is in your car, except that it doesn't use zinc and copper. It uses sulfuric acid and lead, which those equations are more complicated than the ones that we've done, so we don't want to get into those. But in your PDF slides, you have a picture. So every time you have a picture of a battery like that, so every time you have a cell like that, it produces not 1.1 but about 2 volts. And in a car battery, there are 6 of those. They're connected in series, so that produces about 12 volts. And then your alternator will recharge your battery. Your battery is only used to start the car, and then it gets out of the system, out of the circuit, and then it's recharged by your alternator, which will recharge it at a little bit more than 12 volts. Like if you have a gauge, it'll show 13 or whatever. You don't need to know any of this. So let's talk about a galvanic cell. Let's go to the next slide. So galvanic cells use stored chemical potential to do mechanical work, like your car batteries. So they're also called voltaic cells. We'll usually call them galvanic cells. And we'll talk about 2 different kinds of cells. The galvanic cells is the main focus. Towards the end, we'll talk about electrolytic cells, where we talk about how to calculate the number of coulombs that are being produced or that are traveling through, and then we'll use that to do some problems. Next slide. So to introduce this, if you have the 2 scenarios, A and B, that are shown here, how would you be able to figure out which one would actually work the way it's written? So A is copper 2 plus zinc gives zinc 2 plus copper, and B is copper plus zinc 2 plus gives zinc plus copper 2 plus. So they're the opposite. In one of them, in A, the zinc is reducing the copper, whereas in B, the copper is reducing the zinc. So what we want to do is think back to Chem 1311, when we talked about something called the activity series. And I'll get to a slide that shows that in just a moment, but basically the activity series showed us which metals were more active, and so for our purposes, what we mean by that is which metals are the ones that are the most likely to donate electrons to something else. So if you look at the chart, if you have a chart with you, then if you look at the chart, the ones that are the most likely to donate electrons are going to be the things in the first column, especially the things at the top of the first column, like lithium, potassium, and sodium. The reason is because they have one valence electron in the most outer shell that they have, which they are willing to give up to get back to an octet or a duet configuration. So they have a strong, you might want to consider this to be like a pressure to give up electrons. So what we're basically asking here in this problem on this slide is whether zinc or copper has the highest pressure to give up electrons to something else. So there's a couple of ways you can make a chart. One way to do it would be to make the activity series, which typically they aren't done that much. You could also call them tables of standard oxidation potentials, where you would be showing everything in terms of its metal form, like zinc and copper, and then producing whatever the ion is plus some electrons. So for zinc, it would be zinc metal and then an arrow and then zinc 2 plus 2 electrons. And so what they typically do in those kinds of tables is they just rank metals according to how active they are, which is the same thing as saying how likely they are to donate electrons. However, the charts that typically go around in the literature are written in the opposite direction. They're written in terms of how likely something is to be reduced. So you would start off with something like Cu2 plus or zinc 2 plus 2 electrons producing arrow the metal. So in other words, it's the opposite. So we have to learn how both of these charts work in order to be able to predict this. But we can go ahead and we can just say at this point that zinc will reduce copper, which means that A on top here is going to be the way it actually happens. And the way that you can tell that is when you add up the voltages for the two half cells. For the zinc half cell and the copper half cell, you get a positive number. So the positive number or voltage tells us that it will run the way it's written. So A will run the way it's written, B will not, because you get a negative potential when you add the two half cell voltages. All right, next slide. So here is what you would see. The way that these are written would be the way they would be written in a table of standard oxidation potentials. But that's not the way our chart is going to be written, but just so you'll be aware of it, this would be like an activity series. So if you look, zinc has a potential of plus 0.76 volts to go to zinc 2 plus 2 electrons, and copper only has a potential of negative 0.3 volts, which means that zinc is more likely to donate electrons than copper is by a substantial margin. So the way that it would work would be the zinc would run the way it's written here. It would donate 2 electrons, and the copper would be reversed. So instead of being written as Cu going to Cu2 plus 2 electrons here, it would be written the opposite way. It would be written Cu2 plus 2 electrons gives copper metal. And if we reverse this direction of this half reaction, we also have to reverse the sign here, which would go from minus to plus. So this would become plus 0.34 volts. And when we add plus 0.76 to plus 0.34, we get 1.1. And I'm not going to spend a lot of time trying to write with this little thing because this marker is really hard to work with, but we would get 1.1 volts, which is what we did get in the lab. All right, so in other words, zinc's potential to supply electrons is greater than copper's. So how would it be written in a real chart, or not a real chart, but in a chart that's written the way ours will be? Let's go to the next slide. This is how it would be written. So you see everything is written from the standpoint of something that's gaining electrons. So if you look at the top here, you've got F2, which, I mean, that's a halogen, so that's telling you right off the bat that that's going to really want to gain electrons, right? It's the most electronegative element, right? So F2 going to plus 2 electrons going to 2F minus, you've got a huge potential for that to happen. And it's a positive potential, so that's very likely to happen. Whereas the things down here at the very bottom, which are the things like, for example, here at the very bottom right, lithium and potassium here and also sodium here are the things that if you were doing the activity series, those would be at the top, right? So the reason they're at the bottom right here is because we've reversed the direction. So now we're not talking about their ability to be oxidized, we're talking about their ability to be reduced. So they end up at the bottom here, and so they're the ones that are the least likely to actually gain electrons. And the reason is because things like lithium and potassium and sodium don't want more electrons. They want to get rid of the one that they have. Whereas up here at the top left, fluorine has a tendency, a very strong tendency to gain electrons. So that's why it's most so the way that you read this is the most positive thing is the thing that's the most likely to gain electrons. So look at the chart. Which thing is most likely to gain electrons? F2, which is the least likely, Li+. So the ones that we're interested in are in these red boxes. So it's the copper 2+ here and the zinc. So the way that this chart works, it's easiest if you just kind of like remember this little rule. The thing on the bottom reduces the thing on the top. Again, the thing on the bottom reduces the thing on the top. This is the thing on the bottom. This is the thing on the top. So the thing on the bottom, which is the zinc, will reduce the thing on the top, which is the copper. And what that means is that the copper will run the same way it's written here. It will gain electrons, but the zinc down here at the bottom here will actually have to be reversed because it's going to donate 2 electrons. So we have to change it from zinc 2+ plus 2 electrons gives zinc to zinc gives zinc 2+ plus 2 electrons. And that means we have to change the sign here from minus 0.76 to plus 0.76 and then add the plus 0.76 to the plus 0.34 here to get 1.1 volts. Okay, so the rule is the thing on the bottom reduces the thing on the top. So even if you have two things, like let's say you've got this thing right here, the chromium 3+ going to chromium 2+, and then you've got Mg2+ going to Mg, then you can still have a cell made of those two things. The thing on the bottom here, which would be the Mg, would reduce excuse me, the thing on the top, which is the chromium. So the chromium would be written the way it is, and the magnesium here at the bottom would have to be reversed and go in this direction, which means its sign would have to become plus 2.37 here, and you would add that to minus 0.5, so that's going to be like plus 1.87. It's plus, so that means that the cell would work. Okay, so this is the basic idea of the most important part of this chapter. So whenever you get your chart, sometimes they won't give you the whole chart for a problem. They'll just give you the two things that you're interested in, like they might give you the silver 2+ here and they might give you the gold here. Then what you would do is just do the same thing we did. First of all, make sure that it's written in this direction. They might try to trip you up on the final exam, so make sure that it's written in this direction where whatever it is at the left is an ion gaining electrons on the left-hand side of the arrow. And that's telling you that this is a reduction chart. You've got something that's gaining electrons. Make sure it's written this way first, which it almost always will be. And then you want to take the thing on the bottom, reducing the thing on the top, which means the thing on the top is going to stay in the direction it's written, and the voltage will stay the way it is. And the thing on the bottom will have to be reversed in direction, and the sign of its voltage will have to be changed, and then you add them. You add the two voltages to get the cell voltage. So what they'll typically do in an exam would be to ask you to figure out which way it's going to run. So for example, if you have a zinc copper cell, it's going to run where on the left-hand side you're going to have the zinc here. So this zinc right here would be on the left, and then this copper 2+ would be on the left. The 2 electrons are on both sides, so they cancel. On the right, you'll have copper metal, and on the right, you'll have the zinc 2+. So that's how the actual reaction would look, and it would be balanced already because you have 2 electrons for each, but that won't always be the case. And then the voltage is the next thing you would figure out. So reverse the minus 0.76 to plus 0.76 and add it to plus 0.34. And then sometimes they'll also ask you to sketch it. So you always want to put whatever's being oxidized on the left, which in this case is the zinc. The zinc is being oxidized because it's losing electrons. So you put that on the left. So you put the one that has the zinc electrode on the left-hand side. And we do that almost every time. There's one exception, which if I remember, I'll tell you later when we talk about it. But almost like 99% of the time we'll do it where the electron flow will be from left to right, which means the thing on the left is being oxidized. And as we'll see in a moment, the thing that oxidizes, we call that terminal the anode, and the thing that's being reduced is called the cathode. All right, let's go to the next slide. And here we have a picture of what we just said. So we've got zinc in zinc 2+ solution on the left, and we've got copper in copper 2+ solution on the right. So we already determined this, right? That we said that the zinc will reduce the copper. What that means is that electrons will flow out of that zinc electrode, and when they do, they leave left behind zinc 2+, and that drops off the electrode into the solution. So that electrode gets smaller with time, and on the right, those electrons come over to the right-hand side, travel to the edge, and meet up with a Cu2+ and convert it to Cu, which will then join itself to that electrode, so the electrode over on the right will get larger. Notice in the middle there, where that kind of pinkish area is, that's the salt bridge. So that's where you're going to either have negative ions going right to left, or you'll have positive ions going from left to right to complete the circuit. And it's equivalent either way. And then up here at the top, you would have your voltmeter. This thing right here would be a voltmeter, and you just write in your 1.1 volts. So the way that you draw these, be sure you don't forget to put in the salt bridge. Just put it in. You can put it in either the way it's shown here, or you can make a little thing like we had in the lab, like a U-shaped thing like this that you can draw in. And it's very hard to draw with this little marker. And then put the thing that's going to be oxidized on the left-hand side over here. So this is oxidation. This is reduction. Reduction happens at the cathode. Oxidation happens at the anode. Oxidation and anode both start with vowels. Reduction and cathode both start with consonants if you want to use that as a trick. Next slide. So this galvanic cell is a zinc copper cell that produces a potential difference of 1.1 volts. We just said this, the side of the cell where oxidation occurs is called the anode, which is usually 99% of the time going to be the left side. The only exception is when we do concentration cells, where we have a problem that switches them back and forth, and then we leave it the way it is. And then the side where reduction occurs is called the cathode. So the electrons are going to flow from left to right. Next slide. So if we notice the zinc copper cell, the zinc reduces the copper. To figure that out in a problem, you look at the chart, find your two species, and then take the thing on the bottom, and the thing on the bottom will reduce the thing on the top. And the caveat is you have to check to make sure that this is a table of standard reduction potentials. At the bottom here where it says some tables show it in the reverse order, really, I haven't really seen any that give the voltages, but they do list them according to the activity series, but most of the time the charts are shown as tables of standard reduction potentials. Next slide. Next slide. So again, here we have our chart. Next slide. And then this chart is, this slide is just saying that you have to be careful because sometimes they may have two different listings for the same species. Like, for example, for copper 2+, there's 1/2 reaction that is listed with it gaining 2 electrons, but there's another one where it only gains 1. So you have to be sure that you've got the right species with the right number of electrons. Next slide. So basically, here are some basic definitions. Electrochemistry is the study of how we use chemical potential differences to produce voltages or batteries. Redox reactions are reactions that are different from other reactions because they involve the transfer of electrons. Remember, whenever one thing gives up an electron in a reaction, something else has to get it. So the thing that gets the electrons is gaining electrons, it's being reduced, and the thing that gives them up is being oxidized. And then here's the thing that's a little confusing. If something is being oxidized itself, that means it is the reducing agent. And if something is being reduced itself, that means it is the oxidizing agent. Next slide. And then one thing you'll want to remember for all the problems that we're going to do later is that the volts that we're talking about, like the 1.1 volt for the zinc copper cell, the units for that are joules per coulomb. That's energy over charge. Or joules can also be work, but in this case we're looking at it as potential energy over charge, but later we'll also look at it in terms of work. All right, so I would memorize this. 1 volt is 1 joule per coulomb. Next slide. So when we looked at that table a moment ago, that was something that's called the standard cell voltage, which means that these all were done at 25 degrees centigrade or room temperature, at 1 atmosphere pressure, and every concentration of the solutions was all 1 molar. So later on, when we talk about the concentration cells, the Nernst equation, we'll talk about how to figure out what the voltages would be if they were not at standard conditions. And we won't worry too much about the temperature and the pressure, but we will worry a lot about the concentration. So what we're going to look at is how to figure out what the voltage would be or how it would change if we were not at 1 molar concentrations on both sides. Reading down here, kind of in the middle, when a half reaction is reversed, the sign of the voltage is reversed, which we mentioned that before. And notice this right here, when you multiply a half reaction by an integer, the reason you would have to do that would be if the number of electrons in 1 half reaction doesn't match up exactly. For example, if 1 half reaction only produced 1 electron and the other one gained 2 electrons, then you would have to multiply the first one by 2, but you don't change the voltage. It's like if you have a piece of blue paper, then if you cut that piece of paper in half, it's still blue, right? It doesn't matter if you have half a sheet that's blue or 1 sheet. And that's the way it is here with the voltage. The voltage or potential is intrinsic. It doesn't depend on how much is present. And then the very last statement, a galvanic cell runs spontaneously in the direction that gives a positive voltage or a positive value for E naught of the cell. The E naught of the cell here stands for the standard cell voltage. When you see this degree sign right here, it means you did it at 1 atmosphere, 298 K, and you did it with 1 molar concentrations. Next slide. All right, let's look very briefly at line notation. Line notation is just a different way to write these things. So instead of writing them like A2 plus B gives B2 plus A, you do it with lines where we'll see an example. You put 2 vertical lines in the middle to show where the salt bridge would be, and you put the anode reaction on the left. So on the left-hand side of that double vertical line, you would have, for example, what's happening at the anode, which would be like zinc going to zinc 2 plus. And then the double line, and then on the right-hand side, you write the reduction half reaction, which would be like copper 2 plus 2 electrons goes to, and you wouldn't write the electrons, goes to copper. So it just changes the way things appear. Let's go to the next slide. So for example, here, if you have magnesium and aluminum, here at the top is the way we would typically write this. So we've got magnesium plus Al3 gives magnesium 2 plus Al. where this is not balanced. Okay, so you would have to change this to get it balanced, but that's not really the point right now. So here, the two reactants are going to be the magnesium solid and the aluminum 3+, and the two products are going to be the magnesium 2+ and the aluminum solid. So you just break these up and put the aluminums together and put the magnesiums together. So we want the one that's losing electrons on the left, which in this case is the magnesium. So we put the magnesium going to magnesium 2+ on the left and the aluminum 3+ going to aluminum on the right. And then just draw a vertical line between the reactant and the product here and the reactant and the product here. Now, this is a very simple one. There are some of them that are much more complicated, but we won't probably have those or have to worry about them in this class. Just be aware of it. And so what's happening at the anode is, again, you've just got the magnesium going to the Mg2+, and at the cathode on the right-hand side, you just have the aluminum going to 3+ going to aluminum. But you have to be careful. You have to watch it, because notice that even though this thing right here is on the left, it's actually a product, and even though this thing right here is on the right, it's actually a reactant. Okay, let's go to the next slide. All right, now let's kind of transition over into the Nernst equation. So this is from chapter 19 when we talked about thermodynamics. And remember, we said that the most work we can get out of something would be the change in the free energy. So what we're going to do now is, first of all, remember in chapter 19 we started with work equals force times distance, and we converted that over to a form that's more useful when we're dealing with thermodynamic experiments. And we decided that work could be written as minus P delta V. We had to put in the negative sign because of the sign convention, because the work would be negative work because it's being done by the system, whereas the delta V would be positive. So they're always going to be opposite in sign, so just stick in a negative sign. Well, we're going to have the same thing here. We're going to have a third definition of work. So in addition to work equals force times distance and work equals minus P delta V, we want a new definition for this chapter. And that definition is going to be that work equals minus the charge times the voltage. We're not going to actually derive this as we did with the one in chapter 19, so you'll just have to remember this one. So the work is minus the Q, or the charge, times the voltage, or the potential. Again, this minus sign here is the same reason that we put it in chapter 19. It's because whenever we have a positive voltage, then that means that we're going to be doing negative work. So we have to put in the negative sign. All right, the units for charge are in coulombs. A coulomb is 6.24 times 10 to the 18th, what are called charge carriers. In other words, something like electrons. But it wouldn't have to be electrons. It could be positive ions, but almost all the time it will be electrons. So just try to remember this is on the order of 6 times 10 to the 18th. That is called 1 coulomb. You'll want to try to remember that. So 1 coulomb of charge is, if you had electrons, it would be about 6.2 times 10 to the 18th electrons, which means that every time 6.24 times 10 to the 18th electrons go through a wire in your home, that's 1 coulomb. And if that happens in 1 second, 1 coulomb in 1 second, in other words, if you time the number of electrons that are going by a certain point in a wire in your home, and you count off 1 second and count all the electrons, and there's 6.24 times 10 to the 18th of them, that means that you had 1 coulomb of electrons that went by in 1 second, which means you had 1 amp. So amperage is a measure of current. It's the units for current. So to go back up above here, the units would be coulombs for Q. So Q's units are measured in coulombs. And what did we just say about voltage? The units for voltage are joules per coulomb. So when you multiply coulombs times joules per coulomb here, you wind up with joules left over, which is what we want because this is work. So joules are the units for work or energy. Work and energy are just two different forms of the same thing. If you have a joule of energy, you can use it to make, if you have a perfect machine, you can use it to make 1 joule of work. Next slide. So here we have this rewritten in a different way. EMF, or the potential difference V, is going to be the work over the charge, joules per coulomb. So this is what we said earlier, only we just said it was joules per coulomb, where we just mentioned the units, but actually joules would be a unit of work, whereas coulombs would be a unit of charge. So when you have 1 volt, you have basically 1 coulomb of charge, and when you multiply that, or when you apply 1 volt to 1 coulomb of charge, you can produce 1 joule of work. Next slide. So E, or voltage, here would be minus the work over the charge. Again, if you have trouble to remember this, then just remember our definition. For voltage, it's joules per coulomb, which in this case would be, we're going to call it work instead of energy. And then it's per coulomb, and coulomb is a measure of charge. So all we're doing here at the top is we're rewriting something that we've already written several times. And then multiply both sides of this equation right here by Q, and you get minus W equals Q times E. So in other words, the amount of work that we can do, if it were the maximum amount of work, would be the maximum voltage times the amount of charge that we're moving through a current. But in a real process, we lose some of the energy to friction or heat, which means that we'll never be able to keep that maximum voltage through the whole circuit, so it'll be degraded. So if you started off, for example, with 2.5 volts, you might drop down to 2.1. So the real amount of work that you could actually get out of that circuit might only be, instead of 2.5 volts times the charge, it might only be 2.1 times the charge. So we're not really going to worry about this too much, but just kind of notice the difference here. So if you take the amount of work you actually get out of a current or a circuit and divide it by how much you would have gotten in a perfect circuit, that's called the efficiency. And we talked in chapter 19 about this a little bit. We said that there's no such thing as any kind of a machine that can produce 100% efficiency, which is the same thing as saying there's no such thing as a perpetual motion machine. And I mentioned at that time that even 30% would be a good efficiency. And just so happens that I happened to stumble across a YouTube video, actually it was yesterday, about steam engines and how they were replaced by diesel engines. The steam engines were the old kind of things, like if you see in the old westerns, the guy shoveling coal in as fast as he can into the burner, and then that's in a separate compartment, and that will produce steam out of water, and then that steam can be used to drive the locomotive. And that was actually what drove the Industrial Revolution, was just basic steam engines like that. But you had to burn coal, and they weren't very efficient. They were only about 10% efficient. I'll wrap this up because I know this is off topic. When they went to the diesel engine, they combined everything into one unit. So they discovered that if you compress air enough, it gets hot enough that it will actually ignite fuel if you drop fuel in there. So that was the basis of the diesel engine. You just drop diesel fuel in there, it explodes and it pushes the piston back up. Eventually they would replace the steam engines basically completely, and the efficiency of those was about 30%, which is what I had mentioned. So now I think I remember them saying that about 96% of all the transportation of goods in the world is done either, well, it's done by diesel engines, either in trucks or trains or ships. So all of those use diesel engines. Let's go to the next slide. Okay, so very quickly we want to figure out what is the relationship between a coulomb and a mole. So remember, the definition for a mole is that 1 mole is 6.02 times 10 to the 23rd of anything. Whereas we just said that a coulomb would be 6.24, which is about the same as 6. It's roughly the same. They're both about 6, but it's times 10 to the 18th. So that means that if we want to figure out how many coulombs could we fit into 1 mole of electrons? It would be about 100,000, because we would be dividing 6 times 10 to the 23rd roughly by 6 times 10 to the 18th, which is about 100,000. So if you just want to try to remember that, the difference here, we're looking order of magnitudes here. For a coulomb, it's about 6 times 10 to the 18th. For a mole, it's about 6 times 10 to the 23rd. We can fit about 100,000 or 10 to the 5th coulombs into 1 mole of electrons. And we want to use that in some of the formulas that we're going to have. So they give this number, which it's not actually 100,000, it's actually 96,485, and that's the number of coulombs in every mole of electrons. They give this number a special name. They call it F, which is written as a capital F, italicized basically, and that stands for what's called the Faraday constant, where Michael Faraday was one of the early pioneers in electricity, and followed later by his fellow James Clerk Maxwell, who actually developed like the overriding set of equations that govern all of electricity and magnetism that are called Maxwell's equations. All right, so we're going to want to remember this. It will be given to you on your formula sheet. Not that number, sorry, but this number down here at the bottom, 96,485. This number right here is the one that we're going to need. It'll be given to you in your formula sheet. So that is the number of coulombs that we would have in 1 mole of electrons. Next slide. All right, so we've already talked about this, and so what they're going to do here is they're going to talk about the difference between how much work you could produce if you had a real circuit versus an ideal circuit, which I'm not really going to concentrate in on that. But one thing I do want to do is I want to go ahead and help you derive another of our triangle relationships, if you want to call it that. So they're starting off with something we already did a couple of slides ago. We said that E equals work over Q, and it's minus because of the sign convention. And then we rewrote that is that the work is minus QE. What we're going to do now is we're going to break down the Q here, which is the number of coulombs, into 2 parts, utilizing what we just said in the previous slide, which is that there are about 96,485 coulombs in 1 mole of electrons, meaning that if we multiply moles of electrons times coulombs per mole of electrons, we get coulombs, which is what we have right here. So that means we can replace this Q right here with the number of moles of electrons, which we'll write as N, just like in the ideal gas law kind of, times the Faraday constant, which is coulombs per mole. So moles times coulombs per mole will give us coulombs, but it's easier to do the problems if we write it that way. So instead of writing it the way it is here at the top, like that, we're going to write it the way it is here at the bottom right. Work equals minus NFE, where the NF here is replacing the Q right up here. So we're going to be using this thing right over here a lot. We're also going to relate this thing over here to delta G, and we're going to think back to when we did chapter 19. We said that the most work we can get out of a system would be the amount of free energy that's produced, so we wrote that as delta G equals minus W max. Also, we're seeing here that the work is minus NFE, so we can set the delta G equal to the minus NFE, and that's relating something from chapter 19 to something from chapter 20. Delta G is minus NFE, which we'll come back to that. So here's a little problem. So they're basically doing this problem showing that the maximum voltage here was 2.5 volts. Let me go up here and underline it. That would be the maximum potential when you don't have any current flowing through the circuit. But when you actually have current flowing through the circuit, the potential drops to 2.1 volts. So what they do here is they figure out how much work you could do at an ideal voltage of 2.5 versus what you could do at a real voltage of 2.1 volts, and they compare them, and we're really not too worried about that. So let's go to the next slide. So work is never the maximum possible. When you have current, you have by definition friction and heat loss of your energy. So in any real spontaneous process, you're going to always lose some energy just because it's going to be wasted. So here it's going to be wasted through the friction and the heat of the electrons as they go through the circuit. So in other words, the bottom line is the actual work you can get out of a circuit is always going to be less than what it would have been ideally if you just use the voltage of the cell as it would be at rest. Next slide. So this is what I promised we would do next. From 19, remember we said that the maximum amount of work would be the change in free energy, but we have to have a negative sign on one of the other sides there because they're going in opposite directions. So we can rewrite this as what we said here for the cell just a couple of slides back. We said that we can write that as the work for electrochemical cells would be the charge times the voltage. And the maximum here they're going to get rid of here, so I'm just going to kind of mark it out because we're going to remove that soon anyway. So just in this chapter, chapter 20, the maximum work we can get, or the work we can get, would be equal to minus Q times the voltage. Whereas from chapter 19, it would be minus delta G. So what we can do here is we can set this thing right here, the delta G, equal to the thing that we figured. So this is from chapter 19, and we can set this equal to, and we're going to write this here as a positive value, okay, because we're not actually writing this the same way we did in the previous chapter. So we're going to say that the most work we can get out of a system is the change in free energy. So we'll write that as plus and set that equal to this. So we have delta G equals minus QE. And remember, we can rewrite this Q here as NF. So we get delta G equals minus NFE. So what we want is this part right here and this part right here. And this part here for E is from this chapter, and the delta G is from the previous chapter, chapter 19. So this is the second side of our triangle of relationships. We're relating the delta G from chapter 19 to the E, or the voltage, in chapter 20. So we still have one more of these to do, but this is an important relationship here. Delta G will equal the negative of the number of electrons times the Faraday constant times the E of that cell, and you get the E of the cell by just using the process that we used at the beginning of the slideshow, where we just, the bottom reduces the thing on the top, reverse the voltage of the thing on the bottom and add it to the voltage of the thing on the top. That's this E right here. That's actually the E naught, so that's the E at standard conditions. So it's this E right here. It's not necessarily the other one. When you're at standard conditions, which is the way we would be, so that would be this one here. So when you read the values out of the chart, those are at standard conditions. So those E values are written as E naught values because they're showing that the concentrations are basically 1 molar. Whereas this thing up here at the top is the same form as the thing at the bottom, except these are not at standard conditions. So that means that you don't have 1 molar concentrations. It could also mean that you're not at 1 atmosphere, or you're not at 25 degrees centigrade, but usually what we're concerned about is that we wouldn't be at standard concentration, which is 1 molar. So what this is saying is that the maximum cell potential that we can get is directly related to the free energy difference between the reactants and the products, which that's a little heavy, but just try to remember the formula here, which this will be on your formula sheet. And let's go to the next slide. So here we can sum by saying that a spontaneous process, which we introduced in chapter 19, would have a negative delta G, which we said in chapter 19, the delta G includes both the enthalpy and the entropy terms. So it's pretty much a fail-safe or fail-proof mechanism to find whether a process will be spontaneous. So if the delta G is negative, or that's equivalent to saying, as we said in the previous chapter, that's equivalent to saying that the delta S of the universe is positive, those both would tend to spontaneity. In other words, whenever you have that, you have a spontaneous process. Now, in this chapter, we're saying that whenever the voltage of a cell, so if you have a cell, then if the voltage of that cell is positive, then that means it will be spontaneous. Next slide. All right, so here we have an example. At the top, we have Cu2 plus Fe gives Cu plus Fe2 plus. Will it be spontaneous? And I went ahead and entered in here for you the voltages for the two half cells. So what we're supposed to do is look at it the way it's written and see if it would be spontaneous. So the way it's written, copper 2 plus is going to copper, and I gave you the voltage there's plus 0.34 volts, and Fe is going to Fe2 plus. So if you look here at the bottom one here, right here, this is written in the reverse direction here as the way it's written up here, which means that to get it the way it is up here, we have to reverse the way it is down here and write it as Fe going to Fe2 plus, which means we have to change this minus to a plus, add it to the one on top, so plus 0.44 volts plus 0.34 volts is 0.78 volts, and that's plus, and it is therefore going to be spontaneous. If we tried to write it in the reverse direction, we would get a negative value. So you can try that on your own, and if we get a negative value as we do here at the bottom in this parenthesis, then that would not be spontaneous. Next slide. So here we have our equation again, delta G, in this case it's the standard delta G equals minus NFE standard. And to go back to the previous problem, with 2 electrons that are transferred in every atom, then you would have 2 moles. So N here would just be 2, F here would be 96,485, and the standard cell voltage would be what we just figured out, which was 0.78 volts. Remember, we just found that on the previous slide. So to get the delta G value for this, you would multiply minus, and the minus sign's coming from the formula, times 2, which is N, times F, which is the Faraday constant, and then times the voltage. And this is the standard cell voltage. That means we got it out of the chart, not by measuring it in the lab. So when we multiply all of these together, we get minus, and notice the minus sign, 1.5 times 10 to the 5th joules. So because of that negative sign, and since this is delta G, it means it is spontaneous. Next slide. Okay, it's just natural now to go on to concentration cells, so let's go to the next slide. So a concentration cell is different from what we've just been talking about. So a concentration cell means that we don't have two different things. We have, instead of having, for example, zinc and copper, we have the same thing on both sides, which means there is no potential difference, right? So, for example, here in this picture, we have silver electrodes on both sides, which means there's no potential difference between them, which means that you would think there wouldn't be any current flow, right? And that would be correct if we had 1 molar solutions on both sides, but it turns out that we can make a current flow through this cell, but it's just a tiny current, but we can get a little bit of current by changing the concentrations. And this is going to lead us into just kind of naturally the Nernst equation, which is what we have to use to solve this kind of a problem. So this Nernst equation is going to lead us to the third leg of our, or the third side of our triangle. So what we're going to be concerned about here is that, first of all, our standard cell voltage, the voltage of this cell would be 0, because both of these things are the same. There's no potential difference between these two electrodes. However, there's another thing going on here where, for example, on the left-hand side, the concentration of the silver is only 1/10 molar, and on the right it's 1 molar. So let's go to the next slide. So in concentration cells, we write them again most of the time, although one of the work problems we'll have to do it the other way, but the electron flow will also be from left to right. It turns out that that will be written so, I mean, you can actually try to figure this out yourself. In other words, if you start off with 0.1 molar on one side and 1 molar on the other side, what the 1 molar will try to do would be to decrease its concentration, and the thing on the left, the 0.1 molar, will try to increase its concentration until they're the same at whatever concentration that would be, which means the one on the right needs to become more diluted, which means that some of the stuff here on the right-hand side that's Ag plus needs to go away. On the left, it wants to be more concentrated. We need to produce more Ag plus. So some of the Ags need to go to Ag plus. So the way that both of those things can happen simultaneously is if the electrons flow from left to right, and that's what would happen. It's easier, instead of trying to remember all of what I just said, just remember in a concentration cell. Now this is not a regular battery or galvanic cell like we were talking about before. That's totally different. But whenever you have a concentration cell, the electron flow was going to go from the lower concentration to the higher concentration. So you don't have to think about all that. You can just say, okay, this one here is lower than this one, so the electrons will flow from this one right here over to this one right here. All right, so, and then there's another little rule that we'll want to remember, and I'll mention that in a few minutes, about concentration cells. Again, this is only for concentration cells. All right, so whenever you have a concentration cell, you want to put the lower quantity or the lower molarity on the left-hand side and put the higher concentration on the right, and have the electron flow going from left to right, just as our convention has been. So whenever we try to figure out the voltage of the cell, our standard cell voltage here is going to be 0.8 minus 0.8, which is 0. Next slide. So that brings us to the Nernst equation. And remember that I gave you a derivation at the end of chapter 19 that was like 3 pages long, where this equation right here came from. We didn't do it in class because it's just too complicated. So we're going to start with that as our starting point to figure out the Nernst equation in this chapter, which is kind of one of the main reasons we introduced it in chapter 19. So think back, remember that we said that delta G equals minus NFE. Now, that's the thing that we just derived about maybe 6 or 7 slides back. And so we won't go back through the derivation. We're just relating the free energy here to what we said was the expression for work in electrochemical cells, which is this thing right here. But it turns out that we can actually use this thing right here in this more complicated thing over here at the right. So the thing here at the right can be converted to something useful for this chapter if we do the following. What we want to do, and you don't need to remember this, but we want to just replace the delta G here with the minus NFE here, and then we'll replace the delta G standard also, but for that one we're going to replace it with minus NFE standard. So we're just replacing this thing right here with this thing right here, and then we're replacing this thing right here with this thing right here. And then in order to get it into a more usable form, we divide through this entire equation here by minus NF, which means that this part right here will disappear, and this part right here will disappear, and then over here we're going to end up with a denominator underneath this of minus NF, which I'm not going to try to write it. In other words, we're going to wind up with this thing here at the bottom. E equals E naught, or E standard, minus RT divided by the NF there, and it's now minus here, times the logarithm of Q. All right, so this is the Nernst equation in its most basic form. It's more useful if we change T to room temperature and put in the value for F, the 96,485, and then put in the value for R, which is 8.314 joules per mole K. And then also it helps a little bit more if we change logarithm to log. So the way that you do that is you realize that to get log and logarithm relationships, you have to multiply whatever the base 10 log is by 2.303 to get the logarithm. So if we want to replace that logarithm Q with log Q, we can do that if we rewrite logarithm as 2.303 times the log and leave the log in front of the Q and move the 2.303 over into our quotient over there to the left, so that it's going to be something else that we can include. And let's go to the next slide. And this is what we end up with here. This one is E equals E naught minus 0.0591, where that 0.0591 is the algebraic or mathematical result of all those other terms that we put in for the R and the T and so forth, minus 0.0591 over N. And we had to leave the N in there because that can vary. So it can be 1, 2, 3, or all the way up to 6. And then now notice that it's not logarithm Q. And the reason we switched it is because it's easier to work with logs. And also notice here, this is not the constant, the equilibrium constant. It's Q, the reaction quotient. Okay, so we know what that means, right? It's not at equilibrium, but it is the ratio of the products over the reactants. So if you'll look down here at the bottom, we have two reactants right there, but the one here doesn't matter because solids don't have an activity. They can't change in concentration. They're always one. So the only reactant that we care about is this one right here. It's Mn 2 plus to this, and when we write the expression for Q, we would write that as the concentration of Mn 2 plus to the third power. And that would be in the denominator, and then this would be in the numerator. This would be Al3 plus this concentration raised to the second power, and then we'll just forget about this, and we'll just forget about this. So to go back up here to this equation up here, this is called the Nernst equation. It's what we're going to use to solve for concentration cells to figure out what their actual voltage is. So to do that, we have to first of all know what the standard cell voltage is from the chart. We have to know what N is, and we have to know what Q is. N will usually either be 1 or 2 or maybe 3. Sometimes it'll be 6. Most of the time you can very easily figure out what it's going to be. Just as an example, as I said earlier, if one of the half reactions is giving up 2 electrons and the other one's gaining only 1, then you want to multiply the one that's gaining 1 by 2 to get it to 2, so your N would be 2. Where would you get 6? Well, if one of them's giving up 3 and the other one's gaining 2, the only way that you can match those is to multiply the 2 by 3 and the 3 by 2, and that gives 6, so N would be 6 for that one. And then the Q is going to be the concentrations of products over the concentrations of reactants raised to their coefficient power. So for this one, it would be Al3 plus concentration squared over the Mn 2 plus concentration raised to the third power. Next slide. So for this particular problem, they're telling us here that the Mn is 0.5 molar and the Al is 1.5 molar. So here's our equation again. So, and they also told us that the standard cell voltage is 0.48 volts, where they usually will make you do that part. So you'd have to look at the chart and figure out what the standard cell voltage is, just as we've done. To do this, we need the Q value. So the one of these that was the product here was the aluminum. So we write 1.5 to the second power here over the 0.5 here, which is the reactant, to the third power, and then just do the math on this, and it turns out that you should get about 18, and that is going to be your Q, which we now want to take the log of that. So what power does 10 have to be raised to get 18? So it's going to be like 1. I won't even make a guess, but maybe 1.1. Let's go to the next slide. So it's actually 1.26 here, but anyway, so N is going to be, according to these equations here, this is going to be one of those situations which is kind of rare, but notice that here we're going to have 3 electrons for every aluminum and only 2 for every manganese. So what they had to do is they had to multiply this whole top reaction by 2. Everything had across here, everything in this reaction is multiplied by 2, and everything in this one is multiplied by 3. They did that so that they get the same number of electrons here as here, so that they'll cancel each other out. So these will cancel out, which is what we need. But to do that, we had to multiply this one by 2. We had to multiply this one by 3. So the bottom line here is that the number of moles will be 6, where it's the number of moles of electrons that we're concerned about here. So N is going to be 6. So we put that right here. So here's the N. The 0.0591 came from the formula originally. The 0.48 volts was given to us, and the 18 here is what we got when we figured out what Q is. So we took the log of that. Log of 18 is going to be 1.26. Multiply it by 0.0591 divided by 6, and subtract that from 0.48, and you just drop a little bit, notice, to 0.47. Okay, so that's how you would do this kind of a problem. This is a Nernst problem for concentration cells. Sorry, this is actually not for concentration cell, but we'll use this for concentration cells. So for this one, we actually had a real galvanic cell. So this is the way we would use the Nernst equation. Next slide. So here is our third side of our triangle of relationships, where they've taken the equation that we were just using, the Nernst equation, and they set E to 0 and they changed Q to K. And when you do that, the E term drops out, the E without the degree sign, and you're left with just E naught equals 0.0591 divided by N log K, where you're at K now because you're at equilibrium. So what we need to get out of this is that whenever a cell dies, like for example, if you run your cell phone or a transistor radio long enough, eventually the battery will go dead. Then when it's dead, we call that equilibrium, which is a little different. So for an electrochemical cell, we say that it's at equilibrium when the cell voltage is 0. And that's the same thing as saying the cell has died, right? The voltage, if it started off at 5 volts, has gone to 4, 3, 2, 1. If you just keep playing it, eventually it will go to 0. So that's what we're talking about here. When that E without the degree sign goes to 0, we can rearrange that equation and change the Q to K, because now we're at what we're going to refer to as equilibrium. So E naught would be 0.0591 divided by N times log K. And this is what we're going to write for the third side of our triangle of relationships, where this K is coming back all the way from chapter 13 or 15. And this E naught is coming from the current chapter. And so that completes our triangle of relationships. Next slide. All right, and then if we want to find the equilibrium constant, using the same technique we used in the previous problem, this is how we would do it. So we would use that equation that was on the previous slide, and they're giving us here a problem where we're given the two cell half voltages, the half cell voltages. One of them is being reduced, one's being oxidized. So look to see which one of these has the higher voltage, and that's going to be this one. So we want to keep this one on top the way it's written, and we want to reverse the one on the bottom, which is done down here. So we're going to rewrite it as Cr2 plus giving Cr3 plus plus an electron. Change this voltage to positive here. Add them, and we get 0.67 volts plus. But the electron numbers don't match. We need a 2 right there instead of a 1. So we have to multiply this entire thing here, this half reaction, by 2, which is what they've done right here. So when we do that, we wind up with the same number of electrons on both sides. N would be 2. The cell voltage, the standard cell voltage, would be 0.67 volts. And let's go to the next slide. So here is our standard cell voltage. It's 0.67 volts. 2 moles of electrons would be transferred for every one of these reactions. So the N would be 2, and the voltage here would be 0.67. So if you look over here on the right-hand side right there, what I did was I started off with this equation here, which is the way we had it written before, and I rearranged it the way they did. So I divided both sides by 0.0591 and multiplied both sides by N, and I end up with this thing right here. So it's just a manipulation, a very simple algebraic manipulation. But this way it gets the log K on one side by itself. So you don't have to do this if you don't want to. It's just maybe a little bit more straightforward. It's just the same equation written in a different way. So to get log of K here, we multiply the 2 times the 0.67, which we just figured those two things out, and divide that now by 0.0591. So again, we just rewrote it and we get that the log of k is 22.6. And so you would just take your calculator and raise 10 to the 22.6 power to get k. But it's easier if you don't do that. Some calculators won't do it because it's too big of a number. But you can just remember that 10 to the 22.6 is equivalent to 10 to the 22nd times 10 to the 6th. Sorry, 0.6. So it would be equivalent to 10 to the 22nd times 10 to the 0.6, where 10 to the 0.6, if you do it on your calculator, 10 raised to the 0.6 is 4, and then just multiply that times 10 to the 22nd. And that way you don't have a problem with the big numbers in your calculator. So the answer is actually given over here, or also here. Here and also down here is 4 times 10 to the 22nd power. So this is kind of a difficult problem. Next slide. So let's go to a concept check. What is the difference between E and E naught? Well, E is the voltage of your cell right now. Okay, so I mean, like if it's been running for 2 days, then it won't be at its maximum cell voltage, right? So what is it right now? If it was originally 5 volts, then now let's say it's at 4 or 3, then E would be 4 or 3. Whereas the E naught would be what it would have been under standard conditions. When is E equal to 0? When the cell is completely dead. So you let it run and run and run until it went completely dead, which happens at times, like with cell phones. So that's considered to be its equilibrium state, and E would be 0. E naught would not be 0. E naught would still be the same thing it always was. It's just whatever it is at standard conditions with 1 molar concentrations. So the bottom question, when is E naught equal to 0? That is when you have a concentration cell where you have the same metal on both sides. Next slide. Next slide. All right, a concentration cell is constructed using 2 nickel electrodes. So notice here we've got the same thing on both sides. So we have a concentration cell. So E naught will be what? 0. One of the sides has a concentration of 1. The other has 1 times 10 to the minus 4th. Which of these is lower? It's going to be the 1 times 10 to the minus 4th. So if you were going to draw this, you would put that one on the left. That would be the anode where the oxidation would occur, and you would put the concentration of 1 molar on the right. In this case, we need to figure out what Q is. So what we're going to do is we're going to use the Nernst equation to find the voltage of this cell. And the second rule that I mentioned previously that you want to remember is that when you're trying to figure out Q, you always put the smaller number on top, this one, and put the larger number on the bottom in the lower position, so that you're going to wind up here with your Q value here, and I'm going to point to it, is going to be 1 times 10 to the minus 4th divided by 1. Any number divided by 1 is just that number, so Q is 1 times 10 to the minus 4th, and when we take the log of 10 to the minus 4, we get minus 4. So the log of Q will be minus 4. What would N be? So let's look back up at the problem statement. Nickel is in the 2+ state. How many electrons would it gain? 2. So N is going to be 2. So we figured out what Q is. We figured out what N is. So we can now go to the formula and remember here that E naught will be 0 because this is a concentration cell. So the voltage of this cell, which is what we're trying to get, will be 0 minus 0.0591 divided by 2 times minus 4. So we've got a minus times a minus, which is a plus. So we end up with, when we do the math, plus 0.118 volts. So that's only about 1/10 of a volt. So as I mentioned before, these voltages on concentration cells are not very large. All right, so but be sure and remember these 2 rules. So whenever you have a concentration cell, put the lower concentration on the left if you have to draw it, which you probably won't. But you probably will have to do a problem like this. So when you're figuring out what Q is, I mean, you can go through the whole mental process of understanding which one is the product and which is the reactant. but it's easier just to remember this rule. Put the lower number, or the smaller number on top and the larger number on the bottom, and just divide and then take the base 10 log of that. Okay, next slide. All right, here's our triangle of relationships where we talked about this one in chapter 19 here. We talked about this one previously in this chapter. And this one is the way that this looked the way it did. This is like the pure form of the Nernst equation. And then once we changed it by using the thing from chapter 19, we derived it and then we adapted it to this chapter. We got this one. And at equilibrium, this one will become this one, where we're going to change Q to K and we're going to change E to 0 and then rearrange. So really the one that relates the standard cell voltage here to the equilibrium constant is this one right here. So this is actually the one that we would put in that third side, but it comes from this one right here. Next slide. All right, so that's the hard part. Let's go on to some things that are not so difficult. I'm already kind of like out of time as far as my limit that I've kind of put on myself, but I think we can go through these next few slides fairly quickly. So let's talk very briefly about corrosion. I'm just going to mention this as far as the definitions. Galvanizing means that when you make something, like if you make iron pipe, you dip it in molten zinc, and that provides a layer of protection that is not foolproof because it can get knocked off, but it still helps. So whenever you talk about galvanized pipe, like in a house, that just means it's got a layer of zinc around it. So if you don't go around and start chipping away at it, it should last for a while. Alloying means that in the process of actually making steel, you alloy the steel with chromium. That's called stainless steel, and some of you may have sinks that are like that. And it's basically really durable, and it really doesn't rust unless you really do something awful to it, like take a sledgehammer and bang it up or something. And even then, I don't know if it would rust because it's really excellent protection. The one that you're most likely to see on the test, especially the final, is this last one, cathodic protection, because this one relates back to what we've been talking about. Cathodic protection protects steel, and let's go to the next slide. It's easier to see here. This thing right here is protecting this steel pipe up here, or iron pipe, by becoming oxidized itself here. In other words, this is more easily oxidized. So in this case, they used magnesium. So they put it down here and they connect it with a wire to this iron pipe. And what will happen is, instead of this iron pipe getting oxidized and turning into rust, this will get oxidized. And when it gets oxidized, it sends its extra electrons through this wire up into the iron. And that adds an extra layer of protection because you've got all those electrons floating around in the iron pipe. And in the meantime, the magnesium has become magnesium oxide, but no one really cares about that because that's not what is using or what is being used to transport. It's this pipe that we care about. So try to remember this because it usually ends up on the final exam. Cathodic protection means you're attaching something that's more easily oxidized to something to protect it, like this iron pipe, from oxidation. Next slide. All right, then this reverse of what we've been talking about is when you do something like charge a cell phone by forcing a current through it backwards. And to do that, you have to force it through at a slightly higher voltage than the voltage that's typically produced by the cell itself, or it will just start going the other direction. Next slide. All right, so the way that they ask these kinds of problems is they'll typically give you a problem where they want you to figure out, for example, how many grams of some metal can be deposited by electrolysis. So another way that electrolysis can be used, in addition to recharging cell phones, etc., is you can use it for electroplating. So this would be a typical problem that you would see. They'll give you the number of amps, which, remember, amps are coulombs per second. And they'll give you a time, which you would need to convert to seconds. And they ask you how many grams of the particular metal can be deposited. Okay, so let's just do this one. The way you do these is, first of all, you multiply the amperage, which is in coulombs per second, times the seconds to get the coulombs. And then The coulombs don't really help that much in this case, so we want to convert them to moles of electrons. So to do that, we just divide it by the Faraday constant, which remember was a way that we can convert back and forth between the number of coulombs and the number of moles. We said that there are about 100,000 coulombs per mole. In this case, what we want to do is convert it to moles of electrons, which means we want to divide the number of coulombs by Coulomb's constant. And if you want to figure the units out, that would be a very good exercise. You'll end up with moles of electrons. So first of all, multiply the number of amps times the number of seconds to get coulombs. Then divide the number of coulombs by Faraday's constant to get the number of moles. And then you have to look at what you're trying to plate out. Like if it's, for example, Fe3 plus, then you're going to need 3 moles of electrons for every Fe3 plus mole to get Fe, right? So you would have to then divide the number of moles of electrons by 3, or 2, or 1, depending on whatever you're trying to plate, to get the number of moles of atoms. So if it's Fe3 plus, it would be divided by 3. That will give you the number of moles of Fe. And then the last step is just the same step you've been doing since 1311, right? If you know how many moles you have of Fe, how do you convert to grams? You just multiply by grams per mole, or in other words, you multiply by, I think, iron, if I'm remembering right, is 55.6 grams per mole, or whatever it is. You just do that for your last step. Let's go to the next slide. Actually, before we do that, there's actually a problem in this slide that we need to look at real quickly. So go back to the first paragraph up here at the top. Suppose we wish to determine the mass of copper that is plated out when we have a current of 10 amps, that's 10 coulombs per second, and we do it for 30 minutes, which is 1,800 seconds, because you have to multiply 30 times 60 seconds per minute. That's 1,800. So multiply 1,800 times 10, that's 18,000. And then divide that 18,000 by the Faraday constant, which is about 100,000, so that's going to be like 0.2. And then you want to divide that one by 2, so whatever you get there, 0.1 or something like that. And then multiply it by copper's molecular mass, which I think is 63.55. So it's going to be like 6 grams. And don't hold me to that. Let's go to the next slide. So start off here. 10 coulombs per second is 10 amps. And 30 minutes times 60 seconds in every minute is 1,800 times 10 is 18,000, or they rewrote it as 1.8 times 10 to the 4th. That's the number of coulombs, which we need to divide by 96,485 to convert it, because the number of coulombs doesn't help for this particular problem. It does in other problems, but not here. So we need here to get eventually the number of moles of, in this case, I think it was copper. To get that, we have to first of all know the number of moles of electrons. So divide the 1.8 times 10 to the 4th coulombs by 96,485 coulombs per mole, and the units will switch around, and you'll end up with an answer in moles of electrons. And it would be 1.87 times 10 to the minus 1st moles of electrons. You need to now divide that by 2, because it's going to take 2 moles of electrons for every copper atom, mole of copper atoms. So we have to now divide that by n, which is 2. And the way you would know that n is 2 here is because this is copper 2 plus, and it's the only thing we're dealing with. So how many moles of electrons would you have to add to 1 mole of copper 2 plus to get 1 mole of copper? And the answer is 2. So n is 2. Next slide. So 2 electrons per each ion means that we divide by 2. So whatever we had here, we divide this by 2, and we get about 0.1 moles of copper. Now that's how you would do these problems, and I understand that the first time you see this it may seem really complicated, but it isn't. So if you'll just go back through these slides, do it exactly the way I said, then I don't think you should have any problem. If you need help though, by all means email. And then just multiply this by the 63.55 molar mass for copper, and you get, I actually got this one right, so you get about 6 grams of copper. All right, let's move on to the next slide and get done with this. So here's another example, which we'll do very quickly. I'll just go through it like mentally here. I'm not going to actually go through every step, but so We have an unknown metal. What we need to know about this metal here is what number of electrons we would need to have to make 1 mole. And so it's M, where the M doesn't stand for magnesium or anything. It just stands for some generic metal. But notice it's mated up here with NO3, and there's 3 of them. And NO3 is -1. So 3 times -1 is -3, meaning the M has to be +3. So that means that our N is going to need to be 3. And we see this right here and also right here. Okay, so we've got 2 amps, that's 2 coulombs per second, multiplied by the seconds. Well, they give it in seconds, it's 52.8. So 2 times 52.8, that's about 105 coulombs. And then what's the next step? Well, we divide it by Faraday's constant, which is 96485, to convert it from coulombs, which we can't really use here, to moles of electrons. And when we do that, we get 1 times 10 to the -3 moles of electrons, roughly. Divide that by 3 to see how many moles of this metal atom we can make. Not the M3+, but the M. And when we divide this number right here by 3, we get 3.65 times 10 to the -4 moles of M, and then just multiply by its molar mass. However, we don't know what the molar mass is, but we do know what the number of moles is here, and we also know what the number of grams is here in the problem statement. So what do you get when you divide the number of grams by the number of moles in that same volume? You get the molar mass. So if we divide the 0.0719 grams by 3.65 times 10 to the -4 moles, we get 197 grams per mole. And so that turns out to be the molar mass. If you look at your chart, the one that matches up best with that is gold. But that's not really the main point here. The main point is that we just did the same process. They took us in a different route here because they gave us the number of grams and asked us to find the molar mass. But the basic process that we used up at the top here, these first few steps, is the same as on the previous problem. Next slide. So this is the last topic, using the method of half reactions. Next slide. So what we're going to do is we're going to go back to 1311, and remember we balanced redox equations by just kind of looking at them and seeing what charges were being transferred. It was a kind of an ad hoc hit and miss procedure, whereas this particular procedure we're going to do right now, which I'm going to have to do, unfortunately, like real fast because we're absolutely out of time, because these videos need to be under an hour and a half. So I'm going to go through this kind of quickly. So basically what they're saying here is that the longer but the more accurate way to balance redox equations is to split them into 2 half reactions, one for oxidation, one for reduction. You're already familiar with that, right? So we'll write 2 half reactions, and then what we'll do at that point is we'll start to balance those separately and then add them back together at the end. So we're not going to do this one, so go to the next slide. At the end of this one, if we had done it the way we're going to do it, this is what we would add up together to get the final overall balanced equation. We're not going to do this example. We're going to do another one. So let's go to the next slide. So the basic steps are given to you on the next few slides. I'm just going to go next slide, next slide, next slide to get past these rules. And I'm going to show you how to do it by just doing an example because it's easier and faster. But you can come back and read these rules if you want to. Next slide. Next slide. Next slide. All right, so let's do this one together. So we've got CrO72 minus plus SO32 minus gives CrO3 plus SO42 minus. So just very quickly, to do it the long way, but the way that will always give you the right answer, or you could just look at it and just try your luck and see if you get it right. But this particular equation would be kind of hard to do that with. So first of all, we have to divide this up into the CR things and the S things. The S things, like for example, SO32 minus arrow SO42 minus will be 1 half reaction. The CR things will be another. Then we have to figure out which one's the reduction half reaction and which one is the oxidation. So let's do that. So first of all, for the CR207, 2 minus, that means that CR would be 7 times minus 2 is minus 14. Leave 2 of those minus 14 there for the charge on the ion, so that leaves minus 12. So the CRs have to be plus 12 to match, but there's 2 of them, so each one of them has to be plus 6. So we have plus 6 for chromium on the left and plus 3 on the right, which means that it has gained 3 electrons, so it's being reduced. So that's the reduction half reaction. So you would write that. You would write Cr2072 minus giving Cr3 plus. That's it. That's all you write, and then write reduction. That means the other one has to be the oxidation, and for the sake of time, I'll leave that as an exercise for you to see that the S is being oxidized. It's giving up electrons. And the oxidation half reaction would be SO3 2 minus, arrow SO4 2 minus. Then once you get it like that, you want to then balance the things that are not either O or H. You say, well, why do you do that? Well, you just have to remember it, okay? I mean, that's one of the things in this class that I can't explain. There's not very many, but this is one of them. So everything that's not O or H, you have to balance it. So for the CR, you've got 2 on the left and 1 on the right, which means you have to multiply the thing on the right by 2. And then for the S's, you have 1 on the left and 1 on the right. So they're already balanced. So, I mean, if we did everything but O and H, then that gives us a big time clue. What are we going to do next? We're going to do the O and the H. So let's just go ahead and go to the next slide. So here we've separated these out. The reduction one is on the top and the oxidation one is on the bottom. So here's the reduction one and here's the oxidation one. And now we want to balance this for everything except for O and H. So the only thing that we can really do anything with is this Cr2. We have to write a Cr3 times 2 here. So we have to add that 2, and now it's balanced. The S's down here are already balanced, so we don't have to do anything to those. All right, next we want to balance O's. Okay, so this is where it gets a little tricky. So you're just going to have to memorize this. Once you do it a couple of times, it'll come very easily. So just remember this. Instead of adding O's, like for example here on the top up here, we've got 7 O's on the left and we don't have any on the right. So we would think, okay, we need to add 7 O's to the right, but you don't do it that way. In order to make this work, you don't add O, you add H2O. Again, if you ask me why, I just tell you, I have no idea. That's just the way it works. So what we're going to do is add plus 7 H2O over here on the right-hand side. What about here at the bottom? Well, we have 3 O's on the left and 4 on the right, so we're going to need to add 1 more to the left. So we add not O, but H2O. And I'm not going to try to write it out because it takes too long, but it would be H2O. And so let's go to the next slide. So here we see that we've added the 7 H2Os to the right for the reduction half reaction, and we've added the 1 H2O to the left. So what do we do next? So take a look at that for just a second. What's not balanced at this point? Are the O's balanced at this point? Yes. So what's not balanced? H's, right? So again, you'll just have to remember this. When you balance H, you don't just add H. So just as for O, we didn't add O, now we don't add H, we add H plus. So how many H's do we have on the right? We have 14 for the top reaction. So we need to add plus 14 H pluses on the left. So plus 14 H's. I'm not going to write it out. Okay, and then what about the bottom, the oxidation half reaction? How many H's do we have on the left here? 2. How many do we have on the right? None. So we need to add plus 2, not H, but H plus. Okay, see how hard it is to write with this silly thing. So anyway, add plus 2 H plus. Let's go to the next slide. So here we've added the 2 H pluses, and here we've added the 14 H pluses on the left here. Are we finished yet? No, not quite, but we're getting there. So one thing we need to still do before we can re-add these together is we have to get these balanced as far as the charge. So this is the step where we balance for charge. So we have to figure out what the total charge is on the left of each of these and on the right of each, and then make them balance. And the way that you do that is by adding electrons to the side that has the more positive charge. Let's do these together. The top reaction first, here, Okay, this one on the left we have plus 14 minus 2 is plus 12. On the right we have plus 6. That means that we have plus 12 on the left, plus 6 on the right. The left-hand side is more positive, so we have to add electrons to it to get it down to plus 6. How many electrons do we have to add to 12 pluses to get it down to 6? We have to add plus 6 electrons. Okay, so that means we would write plus 6 electrons here, right here. And then on the bottom, on the left-hand side, so we're doing the second one now. On the left-hand side, we have 2 minus, and that's it. On the right, we have 2 minus and 2 plus, but that's 0, because 2 minus 2 is 0. So on the right, we have 0. So to get the right-hand side down to negative 2, we would have to add 2 electrons here. So plus 2 electrons. The 2's are not so hard to make, but the e's are really hard. All right, so let's go to the next slide. So notice this is what we just added here, and here's what we just added at the top. All right, so what we want to do is we want to add these back together to get them back so that it's one reaction that's now balanced, but we can't because we have 6 we want the electrons here to cancel each other, but they don't because we've got 6 on the top and 2 on the bottom. So we've got to multiply the bottom reaction by 3 all the way through. So we're going to wind up with 3H2O plus 3SO3 gives 3SO4 plus 6 electrons plus 6H plus. Okay, and then we'll have 6 electrons here to match the 6 electrons here, so that when we add this reaction to this reaction, we get the electrons to cancel each other out. Next slide. So here's where we're going to multiply the bottom reaction by 3, and this is what we're going to wind up with on the next slide here. When we add these things together, this is what we're going to get when we add these all together. Notice the electrons here are going to cancel. We've got 6 on this side, so subtract 6 from each side and they go away. And then also notice the H pluses. We've got 14 on the left and 6 on the right, so we can subtract 6 electrons from each side here. Here will become 0 and this will become 8, which is what we see right here. And what about the waters? Well, we have 3 on this side and we have 7 on this side, so subtract 3 from each side, so this one will vanish, and we'll be left over here with 7 minus 3, which is 4, which is what we see here. All right, and that's it. So if we were doing this in an acidic solution, then this is going to be our answer, because if we're doing this in an acidic solution, then it's okay for us to have these H pluses hanging around, because there's a whole bunch of them already there, right, because it's an acid. The other thing that you'll need to know for the final is sometimes they'll ask you to do it in a basic solution, and that's easy. You just have to remember that if you did it in basic solution, what are you going to have floating around in a basic solution? Well, what? Basically OH minus, which is going to eat the H plus all up. So for every 8 H pluses, you would add 8 OH minuses here, and that would become 8 waters, because OH minus and H plus is water. But you also have to come over here and add your 8 OH minuses, because you can't just add to one side. So now we've got 8 OH minuses over here on the right. And then we also changed up one other thing, because now we've got 8 waters here, but we've got 4 waters here. We subtract 4 from both sides, and this one would then go away, and this one would become 4. So this would now be 4 waters, and then we would have 8 OH minuses over here. And since I don't have that on a slide, let me see if maybe I can actually try to write that out. And we're going to quit here. So that's the way it would be in basic form, in basic solution. So the only difference is you just add the appropriate number of OH minuses to your H pluses. So if you had 4 H pluses, you would add 4 OH minuses. They would become 4 waters. And then over here you would add the 4, and that's it. All right, so next slide. So we got through this in about an hour and 38 minutes, an hour and 40 minutes roughly, which that's long, but this is also a very long chapter. So before I quit, I want to remind you that you would probably do well to go through the PDFs for this chapter and do all the exercises, because I left out a lot. So this was like 70 slides that I just went through, and there's like 170 in the PDF, and it won't hurt anything at all for you to go through those. There's some material in there about batteries that you can check out, and a couple of other things that I put in there just for grins, the way I usually do. So if you have time, definitely go through those. And anyway, other than that, I'll see you in the Chapter 20 work problems.